I'm gonna use this short video to go over the quiz number 2 study guide. I apologize for running out of time today at the end and not be able to go over the questions of quiz 2 study guide. It's a total of 8 questions. The solution is posted on Brightspace. So I'm gonna go ahead and then share the solution from Brightspace. So I'm currently sharing the screen. So let's get to Brightspace, logging into Brightspace. And then as you all know, there's a module created especially for quizzes and quiz reviews. So under content, locate module on practice quizzes, and this is practice quiz number 2, solutions. So I'm gonna click, and then now let's try to go over. So let me go ahead and then read out loud the first question. Given the premises, if the jacket isn't on sale, then you do not buy the jacket. And the jacket isn't on sale, so use the premises, construct an argument, which is a collection of premises, using the rules of inference to determine what you can conclude, if anything, about whether or not you buy the jacket. Now let's look at the solution. Based on what we are reading, and then as I did comment today, it's important to identify the single prepositions. So I encourage you to start off by identifying them. As I'm reading through the first premise, we have if the jacket isn't on sale, then you do not buy the jacket. I'm going to do another comment based on what I graded and what I saw grading the first quiz. Make sure to use positive premises that are not negated, and then if the single propositions, and then if the premises include statements that are negated, then make sure to define the prepositions by using the original statement, which is the actual statement prior to the negation process. So if this part of the first premise is if the jacket isn't on sale, then the single preposition P must be jacket is on sale. And the second one, Q, you buy the jacket. Now, let's read through the premises. This is the first premise. If the jacket is not on sale, then you do not buy the jacket. So that defines the first premises. If P means the jacket is on sale, then you are going to write not P to represent the statement the jacket is not on sale. If and then means implies. So if then, that means implies you do not buy the jacket. If the statement Q is you buy the jacket, that means not Q. So the first premise is not P implies not Q. Now, the second part, or the second premises are connected together by an and. So it's always worth to underline and. And is the jacket is not on sale. So that means not P. So this is a typical case of modus ponens. The way I look at this, if it is kind of like confusing, remember what modus ponens is as the rule of inference. If P implies Q and P, then therefore Q. So in this case, I have not P imply not Q. So think of not P as being another notation S, and then not Q being another notation W. So you have S applies W and S. So therefore W. So in this particular case, the conclusion should be, that's a typo in there, should be not Q. So if you think this as an S, you define this as, use a new notation S to be close to the modus ponens. So you call this not P to be an S. You call this not Q to be a W. You have S implies W, which is the same as saying P implies Q. And S and P, just to be consistent with the way the modus ponens is, as a rule is defined. Then the conclusion should be Q. So the conclusion should be W, and the W is not Q. So once again, we try to make a correction on this conclusion. This is supposed to be not Q. So that's a typo. This P is supposed to be a Q. And then the verbal statement reflects that this is indeed a not Q. So we conclude that you do not buy the jacket. Okay, let's read the second one. Given the premises, if the cafeteria isn't closed, then you do not have to bring your own lunch, and you do have to bring your own lunch. Construct an argument using rules of inference to determine what you can conclude, if anything, about whether or not the cafeteria is closed. So let's start by defining the single prepositions the same way we did it. So if we say if the cafeteria isn't closed, then prior to the negation of the original statement, which we call the preposition P, the cafeteria is closed. Then you do not have to bring your own lunch, which means Q should be you do have to bring your own lunch. So the first premise is going to be not P implies not Q. The second premise is you do have to bring your own lunch, which is Q. So if we look at the solution of this one, again, the way I look at this, let's use some other notations, because sometimes when you have a negation, that's a notation that is always confusing. So you can call not P, you can call it an S, and you can call not Q statement W. So you think of this as S implies W. And the reason why I'm using this brand new notation S and W is to make sure that we stick precisely with the rules. So we have S applying W. And then the statement Q, so if I call not Q to be a W, then the statement Q is not W. So the reason why I use this brand new notation, which you don't see it in there, but I'm just saying them out loud, to make or rewrite this or rearrange it in the form that looks exactly the same as the modus tollens rule. So once again, what is the modus tollens rule? You have P implies Q and not Q, which means not P. That's what I'm trying to do in this particular case. So if I call not P to be an S and not Q to be a W, then this is S applies W. So therefore, the statement Q is going to be your not W, because if W is not Q, then not W is going to be negation of not Q, which is Q. So S implies W and not Q. Therefore, the conclusion in this particular case should be the conclusion in this particular case. So we have Z implies W or S implies W and not W. According to modus tollens, the conclusion should be not. The conclusion should be not S. So once again, I called for all of you to follow me. I call this not P to be an S. As you're watching this and you're listening to this explanation, you just write this down. So to make sure to write this in exactly the same way as the rule is given, I'm going to call this not P and S, and then I'm calling this not Q W. So this Q is the negation of not Q, which is our statement not W. So this Q means the not W. So now I have exactly the way that modus tollens is given. S implies W, and then and not W. So the conclusion should be not S. But what is not S? Not S is actually P. If I call S to be not P, then not S is going to be P. So that concludes that cafeteria is closed. And these are the two rules that are applied to number 1 and number 2. Now, a different example, number 3. This one requires it's more than 2 premises, and then requires to use the conclusion of the first part, which is part A, and then implement it as a premise into part B to make sure that we can conclude in part B. So let me read the statement. Given the premises, it is knowing today, which is just a single premise. We always combined premises that are not compounded with single premises to create an argument. So it is knowing today If you played soccer, then it was not snowing. And if you played soccer, then you took a shower. So obviously, you see that there are more than two single statement or prepositions in this case that will be defined. So construct an argument using rules of inference to determine what you can conclude, if anything, about whether or not you played soccer. So we make that conclusion, and then the outcome of this conclusion that is going to come out of combining two premises together will be used as a brand new premise to conclude for part B. So let's see how this is going to look like. It is snowing today is my statement P. If you play soccer, so you play soccer today, that is Q. Then if you played soccer, then you took a shower, is my third statement R. So what is my first premise? I'm going to combine the single statement, it is snowing today, which is P, with if you played soccer, then it was not snowing, which is Q, that's you play soccer, implies not P. Because P is it is snowing today. Not P is going to be it is not snowing. It was not snowing today. Now, this is a typical case, very direct of modus ponens. We have Q imply not P and P. The original of modus ponens is P implies Q and not P, and not Q, you get not P. So we have Q implying not P. The opposite of not P is P. So if P implies Q, then the opposite of Q is the second premise, which is not Q. So it's modus tollens exactly. Sorry. Given in terms of statement not P negated, therefore not Q. So the conclusion is you did not play soccer today. Now the conclusion of this one will be combined with the if and then premise, which is if you played soccer, then you took a shower, to create a brand new argument. So we have premise, if you played soccer, which is Q, then you took a shower, which is R. So Q implies R. And then the premise number 2 is the conclusion of part A, which is not Q. Now, in order for me to use modus ponens, this not Q must be a Q in order for me to conclude. Obviously, it's not. So therefore, we're not going to be able to reach a conclusion. So we're not going to be able to say anything whether or not you took a shower today. Here is the modus ponens that allows us to reach the conclusion, which is not the case for part B. Okay, so we are transitioning into the last application of arguments and premises. Given the premises, the elevator is not broken or the escalator is working. If the repair company is here, then the elevator is broken and the escalator is not working. Construct an argument using rules of inference to determine what you can conclude, if anything, about whether or not the repair company is here. Now let's see what the single statements are, or the preposition. We always use the original one prior to the negation process. So therefore, P is going to be the elevator is broken. Q is going to be the escalator is working. And R is going to be the repair company is here. Now we'll start combining them. Since there are 3 single prepositions, we have to combine 2 premises to create an argument, and the conclusion of that combination will be applied into the second combination. We must include a single statement as a premise. So let's look at it. The elevator is not broken, or the escalator is working. So this is connecting by a disjunctive syllogism. So connecting by or, which is a disjunctive logic operator. And then that leads us to somehow creating the scenario of building an argument that is going to require the disjunctive syllogism. So let's see what the first premise is. The first premise is the elevator is not broken, which is not P, because P is the elevator is broken. Connection or, then the escalator is working, which is Q. Combined with one single statement premise, which is the escalator is not working, combined with not Q. So not P or Q combined with not Q. Now let's see the original disjunctive syllogism. If P and Q are combined with P or Q and not Q, then we conclude of the statement that is known as, in this particular case, is known as the disjunctive syllogism, which is not P. So now let's look at this and let's see if that is going to be applied in our case. So P or Q and not Q, therefore P. So now let's see how that's going to look like in our case. We have, instead of P, we have not P, which is going to be part of our conclusion. So if I have a P that is disconjunctive with Q and then connected with the second premise and not Q, then we get just P. So P stays the same. Now I start off with a not P and then combination with Q and then the not Q. So that's going to generate a not P, which means in this particular case, not P, clearly we concluding that the elevator is not broken. Now the single premise will be combined with the second part of or the second premise of this application. What is the second premise? The second premise is if the repair company is here, then the elevator is broken. So if and then, so that's going to be an implication. If the repair company is here, which is R, then the elevator is broken, which is P. So we have R implies P and not P, which is the conclusion of the previous one. This is a typical case of modus tollens. So we have P implies Q and not Q, therefore not P. In our case, we have R implies P and not P. So the P plays the role of the Q. R plays the role of the P, right? If you compare them, that's why you see them side by side. So we conclude not R. Our final conclusion is, therefore, the repair company is not here today. And that's the end of examples or the questions of section 1.4. Now we are transitioning to questions that relate to the proofs or the techniques of direct, indirect proofs and the proofs by contradiction, which is part of section 1.5. Let's start off with example number 5. What we are proving, use a direct proof. Now these directions are going to help you out because by saying use a direct proof, you clearly know the technique that you must apply in order to reach a conclusion. Use a direct proof to show that if n is odd, then n squared plus 9 is even. So in the direct proof is, if I know P, then that applies Q. What is given is n is odd. Then we are proving that n squared plus 9 is even. If n is odd, then odd numbers, odd integers are always given in the form of 2k plus 1 for a quotient k for some k. So we are going to show that n squared plus 9 is an even number. So it's going to be given in the form of 2m. We cannot use k because we already used k to represent n being an odd number. So what I do is I start off with n squared plus 9, and then I replace n by 2k plus 1. So we get 2k plus 1 to the second plus 9. Now 2k plus 1 to the second is 2k plus 1 multiplied by itself. Due to foiling, if you do that, you get 4k squared plus 4k plus 1 plus 9, which I can write it as 4k squared plus 4k plus 10. I factor out the 2 because I always need the 2 outside parentheses. And then inside parentheses, I get 2k squared plus 2k plus 5. So what I'm going to do is I'm going to call this m or L. I actually operated with L in class. So this n squared plus 9 is equals to 2m or equals to 2L, which means that n squared plus 9 is even. Okay, now the next one, number 6, is the case of an indirect proof. Use an indirect proof to prove that if n squared plus 6 is even, then n is even. Now, when you use indirect proof, you always start by making an assumption and you prove by contradiction. Notice that the statement with an n, which you know that if is defined and has a definition related to this, an integer, is part of the conclusion. So that's a clear indication that proof by contradiction, the indirect proof must be used in this case. So you have to make an assumption, starting off with n being even. That's what you're trying to prove. What is given is n squared plus 6 equals even. That is given. This cannot be changed. Now, knowing that this cannot be changed, my goal is to show that n is even. So I'm going to start off by making an assumption. Assume that n is not even. So that means n is odd. So that kind of like reverses the direction. So I'm making this, if this is my statement P, I'm making this a not P. If I'm assuming that n is odd, since I assume that n is not even, then n is going to be in the form of 2k plus 1. So I'm going to take this n equals to 2k plus 1. I'm going to plug it in into n squared plus 6. I'm expecting that even though I plug in this number, I'm still getting even. Let's see if that's going to be the case. So if n is odd, then n is 2k plus 1. Plugged in, we get n squared plus 6 becomes 2k plus 1, the quantity in parentheses squared plus 6. Again, through foiling, this 2k plus 1 squared, which is 2k plus 1 times 2k plus 1, is 4k squared plus 4k plus 1, still plus 6. I can write this as 4k squared plus 4k plus 6 plus 1. You see that 1 and 6 are swapped or interchanged. Why? Because 4k squared, 4k and 6, they all share a 2, so they have a common factor 2 that allows me to factor it out. So I get 2 out. What remains inside is 2k squared plus 2k plus 3. I still have a plus 1. And then I'm going to call this expression inside parentheses an m. So therefore, I got n squared plus 6 is in the form of 2n plus 1, which indeed is not even, but is odd. Knowing that n squared plus 6 is given as even, that's a contradiction that shows that whatever I assumed is incorrect. Remember, I assumed that this n is not even, but is odd. But that is not true. So therefore, n is even. So if n squared plus 6 is even, then automatically we just proved that n is also even. Now the next one is a typical example I did in class today with one of 13 individuals trying to show that 2 of them were born, among the 13 were born in the same month. And this is a proof by making using proof by contradiction, making an assumption that contradicts what you're trying to show. So you have a drawer full of loose socks that come in 7 different colors. Prove that if you choose 8 loose socks, then you must have at least 1 pair with the same color. So what is given, and then again, I'm using the same design of the solution, using the square boxes, or you can call the rectangular boxes, representing the drawers. There are 7 drawers all together, and they're full of loose socks. They all come in 7 different colors. So I have 1 drawer for each color. Now my goal is to prove that if I choose 8 loose socks, then I must have at least 1 pair of socks of the same color inside the same drawer. So I'm gonna call colors loose socks: yellow, green, red, orange, black, blue, and purple. There are 7 different colors. Then I'm gonna place the color yellow in the box 1, color green in box 2. So these are the drawer representing, the boxes are representing the drawer. Color 3 is red, 4 is orange, black is 5, blue is 6, and purple is 7. Now, our goal is to show that if you choose 8 loose socks, then you must have at least 1 pair with the same color. So I'm going to make this proof by assuming the opposite, and that's a contradiction. And then show by my assumption is going to contradict the given information. So here's what I'm assuming. If we choose 8 loose socks, then no more, by saying at least 1 pair with the same color is going to belong to the same drawer, we are making an assumption that two of the same colors are not going to be in the same drawer. So in other words, no more than one color is in the same drawer. And what I do is I start picking the loose socks, checking their color and placing them into the right drawer. So I pick one, let's say it's yellow, I place it in box 1. I pick the second is green, I place it in 2. I still have remainings. I pick another one, that's number 3, pick, that's red, and then I do the same thing with orange. I got to purple, so I picked all 7, but I have to pick 8 loose socks, so therefore pair of socks. So therefore when I get to that number 8, I simply ran out of the boxes. These are the only colors I have, 1 through 7, that are clearly displayed. So when I pick that number 8 remaining, that number 8 is going to be one of those colors, let's say green. So I have to place that number 8 with the number 2 in the second drawer. So therefore, we clearly showing the contradiction. At least one pair with the same color is going to be in the same drawer. Very similar to the one I did in class today with the months that individuals were born in. So we have 2 loose socks of the same color in the same drawer. And now let's get to number 8, which is the last one. We define the rational numbers today as the ratios of the form P over Q, where P and Q are both integers, and then the ratio P over Q must be in the lowest terms. So now what we are proving is prove that the product of any 2 rational numbers is rational. So I'm going to pick 2 rational numbers. I'm going to call one of them M and the other one N. By definition, they're given as the ratios. First one, I'm going to call it P over Q, where P and Q are integers, and then P over Q by definition must be in the lowest terms or simplified. And the second number, I'm going to call it N, and the ratio S over T. I cannot use P and Q because they're already used to represent the first rational number, where S and T are integers, and then the ratio S over T is, again, in the lowest terms, which means simplified. We are trying to show that their product, which in this case is going to be product of the first number times the second, M times N, is also a rational number. So if M is P over Q and then N is S over T, their product is going to be multiplying P over Q times S over T, which is P times S over Q times T. I'm going to define the product P times S to be U and Q times T to be V. So this is indeed in the form of U over V. Now, this is something that one of your classmates brought that up, Mr. Bang today. He asked me, are we proving if the sum of integers is an integer or the product of integers is an integer? Very briefly, in class on Thursday, I'm going to show why the product of 2 integers is an integer. But for now, let's make an assumption in all these cases, and then everything that I did in class, we assumed all these things are true. So if P and S are integers, then their product is also an integer. If Q and T are integers, their product is also an integer. So we have U is an integer, V is an integer. So I was able to write the product of these 2 rational numbers in the form of U times V, which is the ratio of 2 integers. U and V are integers. Now the question is this in the lowest terms? Obviously, P, Q, S, T, they don't have anything in common because this is how the ratios are defined. So these numbers are in the lowest terms already. So since they don't have anything in common, U over V is going to be in the lowest terms. And that shows that the product M and N, M times N, is also a rational number because it's defined in the form of a fraction U over V, where U and V are integers, and then U and V is in the lowest term. And that's it. So I'm going to stop sharing. Once again, this solution can be located As I mentioned, go to content and practice quizzes and then look for solutions of quiz number 2. There's a typo in the front page that I explained. When you do the premises and the conclusion uses modus ponens, the very first one, number 1, it's supposed to be not Q, the conclusion. It's a typo. It is not P. That's a mistake. Okay. So I'm going to stop sharing and then stop the recording.